This is the first video for the Chapter 6 notes. Chapter 6 is on normal probability distribution, and this is dealing with continuous data. We saw in Chapter 5 discrete data, so this time we are dealing with continuous data. Section 6.1 is the standard normal distribution. There's a few stars to start us off, and it says the total area under the any density curve is equal to 1. So there is a correspondence between area and probability. And that's a big key idea that we have for this unit. So first type of distribution that we're going to talk about in Chapter 6 is uniform distribution. This is a continuous random variable that has values that are spread out evenly over a range of all possibilities. A uniform distribution does not occur very often just in real life. We mostly are going to see the normal probability distribution, but we'll get to that shortly. This one's just easier to kind of start off and explain some key ideas with. So there is a graph given here, and you'll notice that it is consistent all the way across the top of this rectangle. And again, remember your total area under that curve, under that straight line, area is equal to 1. So the example right below says the reaction time x in minutes of a certain chemical process follows a uniform probability distribution with x between 5 and 10. Says draw the graph of the density curve. And so for this, it's just like up above. We're going to have our probability on the side. We did density curves or histograms in our previous chapter, Chapter 5. And then this is going to be x is our random variable, which is in minutes. And so 1, 2, 3, 4, 5. This actually starts at 5 since we know x is between 5 and 10. So 6, 7, 8, 9, 10. And so I'm going to go ahead and, because I know it's uniform, draw my rectangle here. And these can be split into equal pieces. And so since the area under the density curve is always equal to 1, that means that each of these little pieces is 1/5. And so that means that this corresponding height would be equal to 1/5. Since each of those little rectangles is 1 unit, since this goes to 6, to 7, to 8, to 9, and then to 10. So make sure that you have both your axes labeled. And then part B says, what is the probability that the reaction time is between 6 and 8 minutes? So the probability that x is between 6 and 8 minutes, you would add up those two rectangles that we have, so between 6 and 8, and you would get 2/5. For the next one, it says what is the probability that the reaction time is between 5 and 8 minutes? So the probability that x is between 5 and 8. And you'll notice that this time it's going to be a little bit more of an area. Between 5 and 8, those are actually 3 of those rectangles, so this equals 3 out of 5. And then the next one says, what is the probability that the reaction time is less than 6 minutes? Well, less than 6 minutes, here's 6 minutes, and less than is going to the left. So the probability that x is less than or equal to 6 is equal to 1/5, since there's only one rectangle that is less than or equal to 6. Right below this is our big key idea here, which is on normal distribution. It says if a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, such as the graph that's given here, then if you split it in half, your total area under your graph is equal to 1. So that means each of these pieces would be equal to half, and this is because our total area is equal to 1. And then in the middle is going to be your mean. And then a key idea here that we've already seen for the past few chapters is we can go out 3 standard deviations each way, and that includes 99.7% of our data. So we can go mu minus 3 sigma, mu minus 2 sigma, mu minus 1 sigma, likewise mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. So there are some properties right below this of our normal density curve. Number 1 says it is symmetric about the mean mu. That means that the left side of mu and the right side of mu are identical. and have the same area. Number 2 says because the mean is equal to the median is equal to the mode, the curve has a single peak and that the highest point occurs at mu. 3 is that key idea again, that the area under the curve is equal to 1. Number 4 says the area under the curve and to the right is equal to the area under the curve and to the left, which is half, or 0.5. Number 5 says as x gets larger and larger, the graph approaches but never touches the horizontal axes. And this is also the same as going to the left. And then the empirical rule holds true. So a key thing here to make sure you note and make sure you have this starred a bunch of times is that on the My Open Math homework, quizzes, and exam part of our class, it's going to ask for you to state what x is following. And so it will have this written as x is approximately normal, and then it's going to give you 2 blanks that you are going to be filling in. This is just a check to make sure that you understand and you have read the problem. So in the first blank, you need to put in the mean, and in the second blank, you need to put in our standard deviation. The example right below says the lives of refrigerators are normally distributed with a mean equal to 14 years and a standard deviation equal to 2.5 years. Part A says to draw a normal curve with the parameters labeled. So first of all, we know it's a normal curve, so that means you need to draw your bell-shaped curve. You will be asked to draw these types of curves on a test, so you want to make sure that you get used to drawing them and how to set them up. So in the middle is the mean. And since we know that our standard deviation is equal to 2.5, remember we can go 3 standard deviations to the right. And to find those numbers, we just keep adding the standard deviation, which is 2.5. So 14 plus 2.5 is 16.5. 16.5 plus another standard deviation of 2.5 is 19. And then adding another 2.5, we get 21.5. Likewise, we're going to go the opposite direction and subtract 2.5. So 14 minus 2.5 is going to be 11.5. Another standard deviation, so subtracting another 2.5 is going to equal 9. And then another standard deviation we get, subtracting 2.5, would be 6.5. Part B says to shade the region that represents the proportion of refrigerators that last more than 17 years. So more than 17 years. So for this, we're going to put a line at 17, which is a little bit larger than the 16.5. It's hard for me to label it down there. I'm going to put the 17 up above. And since it says more than, I'm going to be shading this curve to the right. The reason I'm shading it to the right and not the left is because it says more than, and more than means greater than. So what I have shaded here is that area under the curve, which again represents a probability that they are going to be lasting more than 17 years. Part C says suppose the area under the normal curve and to the right of x equals 17 is equal to 0.1151. So this shaded area that we just have tells us that this is equal to 0.1151. It says provide 2 interpretations of this result. So one interpretation would be using that number that we have, that's 0.1151, which is equal to 11.51%. We can either discuss it as a percent or as a decimal. A lot of students like to talk about things in terms of percents. It just is a little bit more tangible. So 11.51% of fridges last more than 17 years. Well, if we know the total area under the curve is equal to 1, then we can find the area of it being less than 17 years. And we would do this by doing 1 minus that area that we have to the right, or using the complement idea that we've seen in previous chapters. So the second interpretation, if you do 1 minus 0.1151, we get 0.8849, which is equal to 88.49% of fridges last, and now it's not more than 17 years, but this time it's going to be less than 17 years. So those are our two interpretations. Again, remember the total area under that curve is equal to 1. Right below this, it says Table A2 provides the areas under a normal curve less than a given value. In order to make one table applicable to all data, we must standardize our random variable. This means we must convert our random variable to a z-score. The random variable z then is said to have a standard normal distribution. So standard normal distribution, again, is where you would have your z-scores. And we have our mean is equal to 0 and our standard deviation is equal to 1 like we saw in the previous chapters. And so that means that in the middle you would have your mean, which is 0. Going 3 standard deviations to the right, we would have positive 1, positive 2, and positive 3. And then going 3 standard deviations to the left, we have negative 1, negative 2, and negative 3. And so right below this, it says standard normal distribution must have the following 3 properties. First one, the mean must be 0. Standard deviation must be 1. And then also we are going to use z-scores, which are going to be x minus the mean all over the standard deviation. And again, this is called a z-score that we saw a few chapters ago. So a z-score is a distance along the horizontal scale of a standard normal distribution corresponding to the number of standard deviations above or below the mean. The region under the curve and the total area under the normal curve is equal to 1. Then we can use table A2 in the textbook to find the area to the left of the value of x in the distribution of x. To find the area to the right, we would have to use the complement rule since the total area is equal to 1. Normally, z-scores are rounded 2 decimal places unless otherwise stated. Right below, it says steps for finding area under a normal curve by hand or with StatDisk. And StatDisk is going to be the key thing here since this is going to be what we use to do our projects. And so in order to do this, our steps are going to be 1, to draw our normal curve and shade in the desired area. Again, use those keywords like less than, more than, that we saw last chapter. Step 2 is going to be converting our value of x to a z-score using our z-score formula. And then use table A2 to find the area to the left of the z-score of the probability distribution function. And this is also for us, it's going to be in the normal distribution on StatDisk. So table A2, we do not use in our course. Instead, we use graphing calculator. For our projects, we do use StatDisk. So make sure that you ask if you have any questions with this. At the top of the next page, it says, for our course, we will use a graphing calculator to compute probabilities of normal random variables. So again, we do not have to worry about that table, which is nice. So we have listed as our steps to find the probability of a normal random variable with a TI-8384 graphing calculator. Step 1 is to draw your normal curve and shade in the desired area. Step 2 is going to go to second, then bars on your graphing calculator, which is distributions, and then go to 2, which is normal CDF. Then you need to enter in your lower bound, your upper bound, your mean, and your standard deviation. A lot of times our graphs go on forever to the left or forever to the right, and remember, it never touches that horizontal, so technically it goes on forever. And so these are ways to do our infinity is pretty much how we're telling the calculator to think of this. So there's a couple things to know. One is going to be the E that is in here is not the letter E that shows up on your calculator. You need to find your button that has a comma, and above that it should say EE. And that's the button that we're going to have to use, is that one. And the comma button is right above the 7. So we'll say right above 7. So the little image next to this is the TI-84 that is in our marks. And our marks center is the one that is our free tutoring center that is on campus at Mount SAC. And they have graphing calculators that you can go in and borrow for the day. So it's listed instead of horizontally, it's listed vertically. It says lower, upper, mu, and then sigma for your standard deviation, and then paste is what you would go down to hit enter on. So the example right below says determine the area under the standard normal curve around 4 decimal places. So first thing is it does ask for area. Area is the same thing as probability, and it also says standard normal curve. Remember, with the standard normal curve, you know the mean is 0 and your standard deviation is 1. And so for this one, it says A lies to the left of Z equals negative 0.43. So I'm going to have to draw my bell-shaped curve, my normal curve. And in the middle, draw a line. That's where our mean goes. And since this is a standard normal curve, the mean is 0. And my value that I have for Z is negative 0.43, which is smaller than 0. So we're going to put a line over here anywhere that you think it is. Remember, you kind of know where 1 standard deviation is, 2 standard deviations, and so forth. So negative 0.43. And it does say going to the left. So I'm going to shade my curve going to the left. And so for this, it goes on forever to the left, which is technically negative infinity. But since we don't have an infinity button on our calculator, we do need to use the negative 1 E99 that is stated up above. And so in order to do this, we have to find the probability that Z is less than or equal to negative 0.43. We're going to go to normal CDF on our calculator. It goes lower bound, upper bound, mean, and standard deviation. So our lower bound is that negative infinity, but again, we type it in as negative 1 E99, comma, where does the shading stop? And the shading stops at negative 0.43, comma, the mean, which we know is 0, and the standard deviation is 1. On the graphing calculator, we are going to go to second vars, and then we're going to go to normal CDF. On here, you're going to enter in your lower bound, which is negative 1 E99. Negative is the negative that's underneath the 3. It has a parenthesis around the negative symbol. And then we're going to take 1. And then E, you need to go to second, comma. And it should put an E on there. And then you're going to type 99, comma. Our upper bound, which is going to be negative, again, that negative is the one that's underneath the 3, and we have 0.43, comma, our mean, which is 0, comma, standard deviation, which is 1. Close your parentheses, select enter, and then round your answer correctly. From the calculator and rounding 4 decimal places, we get 0.3336. So that area or that probability at negative 0.43 and shaded all the way to the left is equal to 0.336, or like almost a little over a third of our graph. Part B says that it lies to the right of Z equals negative 1.14. So again, we're going to draw our curve. Draw your normal curve. In the middle, we're going to put 0 again because we do know it's a standard normal curve. And this time I need to put on negative 1.14. And this time I'm shading to the right. So if you look at this, you're shading more than half of that graph. So kind of using that common sense check when you get your answers, you should know that this is going to be a relatively larger decimal. Remember, the total area is equal to 1, so this should be something larger. And we're asked to find the probability that Z is greater than or equal to negative 1.14. And again, we have to go to normal CDF. The shading starts at negative 1.14 and goes on forever. And forever to the right is positive infinity, but we have to use 1 E99. So we have 1 E99, comma the mean, comma the standard deviation. On your graphing calculator, you're going to go to second vars, normal CDF. Our lower bound on this one is negative, which again is the negative is the one with parentheses around it and underneath the 3. negative 1.14, comma, our upper bound, which this time is 1e99. So type 1, and then to make e, which is our exponential, show up on our graphing calculator, we need to hit second, comma, and it should put the e on your calculator, 99, comma, mean, which is 0, comma, standard deviation, which is 1, close your parentheses, select enter. You get your answer, and then round 4. From your graphing calculator and rounding 4 decimal places, we get 0.8729. Right below this, it says sometimes we want to find the value of a normal random variable that corresponds to a certain proportion, probability, or percentile. So it's almost like going backwards. So this time instead, I would have given you that area amount, like the 0.8729, and asked you to find what the value is where it stopped at or started at. And for this one, it would have been z is equal to negative 1.14. So right below this has the steps on how to do this with a calculator, and steps for finding the value of a normal random variable with the TI-8384 calculator. First step, again, is going to be to draw our normal curve and shade in that corresponding area. Then we're going to go to second vars, go to number 3, which is inverse norm, or INV norm. And then we're going to have to enter in the area to the left, our mean, and our standard deviation. Some of us are going to have a calculator with a little different setup, or if you borrow one from the marks, it looks more vertical. It says area, mu, sigma, and then it also gives you an option. You would select one of these, one only. The one that we're going to leave it on is left, and the reason why is because our notes are always going to be using it as to the left, and so that in that way you have it set up and you know how to use this regardless of what device you're using. The example right below says, given that z is a standard normal random variable, find the z value for each situation. Round 2 decimal places. So again, z is a standard normal random variable. That means our mean is equal to 0 and our standard deviation is equal to 1. And we're asked to find that z value. So this one, part A, says the area to the left of z is equal to 0.9750. So we need to first draw our normal curve. And in the middle, since I know that the mean is equal to 0 and the standard deviation is equal to 1, the mean goes in the middle as 0. And then I have to think about where to put z. I need to shade to the left. And it has to be 0.9750, so that's quite a bit of area. So I know that z is going to be pretty far to the right, because if I shade it, it needs to be most of that graph shaded. And again, I'm shading to the left because that's the way that it says to shade for this problem. I also want to note that z is on the right side of 0, which means that it needs to be a positive number, and that's a nice way to kind of check this. So z is equal to inverse norm, or INV norm, area to the left. And this area that we just shaded is given to us. This is 0.9750, comma, and then we put our mean and our standard deviation, which are 0 and 1. On the graphing calculator, we're going to go to second vars, inverse norm, it's number 3 on my graphing calculator app, INVNORM. And we're going to type in the area to the left, which was 0.9750, comma, the mean, which is 0, comma, the standard deviation, which is 1, comma, close our parentheses, select enter. And then this one we need to round 2 decimal places. From the graphing calculator, we get 1.96. Part B says the area to the right of z is 0.5314. So again, drawing our bell-shaped curve, our normal curve, I'm going to put 0 in the middle. And this time I'm shading to the right. And so I need to shade a little bit more than a half. So I know that z is going to be somewhere over here on the left side, since when I shade it to the right, it's a little bit more than half of that graph. So z is equal to inverse norm, area to the left. Well, since the area to the right that we had shaded is 0.5314, I need to find the area to the left of it. And I'll put that in a different color here. And to do this, we need to do 1 minus 0.5314. And so when you subtract that on your calculator, you get 0.4686. And then our mean is 0, standard deviation is 1. On the graphing calculator, we're going to go to second vars, inverse norm, INVNORM. We're going to type in the area to the left, which is 0.4686, comma, the mean, which is 0, comma, the standard deviation, which is 1. Close your parentheses and select enter. Places we get negative 0.08. And we do have z a little bit smaller than 0, so it does make sense to get a negative answer for this. Right below it, it says critical value. For a standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. Notation, the expression z little alpha, z sub alpha, denotes a z-score with an area of alpha to its right. And again, since it does say standard normal, that means that in the middle, our mean is going to be 0. And that means that if you had a value of z sub alpha, shading it to the right is going to be an alpha size area. So using this idea for the example right below, it says find the value of z sub, and it says 0.025. So for this, I'm going to go ahead and draw my normal curve, put 0 in the middle, and it says the area to the right is equal to 0.025. That's pretty small, so I know that the shading is going to be just a little bit, and this is going to be my z sub 0.025. That would be there. And this little area that we shaded here is 0.025. So to find that area to the left of it, we have to do 1 minus 0.025. When we do that, that unshaded area on this graph is going to be 0.975. So to calculate the z sub 0.025, we're going to use inverse norm, area to the left, which is 0.975, the mean, and then the standard deviation. On the graphing calculator, we're going to go to second vars, go to inverse norm. We're going to type in the area to the left, which is 0.975, comma, our mean, which is 0, comma, our standard deviation, which is 1. Again, the mean is 0, standard deviation is 1 because we do have z in there, and that is by definition the mean and the standard deviation. From the graphing calculator, we get an answer of 1.96. The example right below says assume that the random variable x is normally distributed with a mean equal to 50 and a standard deviation equal to 7. Compute the following probabilities and draw a normal curve with the area corresponding to the probability shaded. Round 4 decimal places. So the first thing to note on here is that we are dealing with just a normal distribution. It does not say standard normal, and that's because it tells us the mean and it tells us the standard deviation. So they're not equal to 0 and 1. This time the standard deviation is 7 and the mean is 50. So the first one that we have is the probability that x is less than or equal to 58. And let's go ahead and draw our bell-shaped curve, our normal curve. And this time in the middle we put our mean, which is 50, that was given to us. And the number that we have in the problem is 58, which is larger than 50. So I'm going to put on 58. And the symbol that's in here is a less than or equals to, which means I'm going to be shading to the left. So in order to calculate the probability that x is less than or equal to 58, we're going to use normal CDF. Where does the shading start? And you read this just like how you read a book, and that's off at negative infinity. Remember, infinity, we use -1 E99, comma, where does your shading stop? And as you're going to the right, we stop shading at 58, comma, the mean, which is 50, and comma 7 for our standard deviation. On the graphing calculator, we're going to go to second, vars, normal CDF, type in our lower bound, which is -1 E, which again you need to do second, comma, 99, comma, we have 58 as our upper bound, comma, our mean, which is 50, comma, our standard deviation, which is 7. Close your parentheses, select enter, and we get our probability that we need around 4 decimal places. From the calculator, we get an answer of 0.8735. Part B is asking for x greater than 65, so the probability of that. So first thing we're going to do is draw our normal curve and put our numbers on and shade. So the mean again is 50, and this time it says 65, which is again farther to the right. And our symbol that we have says greater than, so I am going to shade to the right. Remember, this goes on forever to the right, which is infinity. And so the probability that x is greater than 65 is equal to normal CDF. Where does the shading start? As you read this from left to right like you would read a book, the shading starts at 65, and it goes on forever to infinity, which we use 1E99. Our mean is 50 and our standard deviation is 7. On the graphing calculator, we're going to go to second, vars, normal CDF. This time our lower bound is 65, comma, our upper bound, which is 1E99. So we need to type 1. E we get by going to second, comma, type 99, comma, the mean, which is 50, comma, standard deviation, which is 7. Close your parentheses and select enter. From here you get your probability. Make sure to correctly round 4 decimal places. From the graphing calculator, we get an answer of 0.0161. Part C says find the probability that x is between 56 and 68. So again, drawing our bell-shaped curve, putting the mean of 50 in the middle. The two numbers that we have here are 56 and 68. Those are both larger than 50. So we have 56 and 68, and this would be between these two values, so shading that area between those two. We're now going to find the probability that x is between 56 and 68, and we still need to use normal CDF. So where does the shading start? As you read from left to right, it starts at 56 and it ends at the number 68, comma, the mean and the standard deviation, putting in 50 for the mean, 7 for the standard deviation. On the graphing calculator, we're going to go to second, vars, normal CDF. Our lower bound for this one is 56, comma, our upper bound is 68, comma, our mean is 50, comma, standard deviation is 7. Close your parentheses, select enter, and we get our probability that you need to round correctly to 4 decimal places. From the graphing calculator, we get a probability of 0.1906. The example right below says find the value that separates the bottom 2.5% and the value that separates the top 2.5% on a standard normal distribution. And again, anytime you see that word standard normal distribution, you know the mean is 0 and the standard deviation is 1. It also tells us to round 2 decimal places. So the first thing let's do is draw our curve. So draw your normal curve. Since we know the mean is 0, I'm going to put 0 in the middle. And it wants the top 2.5%, which again is going to be 0.25, and the bottom 2%, which is 0.025 as a decimal. So those are pretty small little areas. So I'm going to draw my 2 values out here. So the bottom little shaded area is 0.025, and that little top part is going to be 0.025. And I need to find both of these values. I'm going to call this one Z1 and the right one Z2. And so since now we're trying to find out the area we were given that, or the probability we were given, we're going backwards. So Z1 we have to find and Z2 we have to find, and both of these we're going to be using inverse norm. So inverse norm works as area to the left, and the area to the left of Z1 is 0.025. The mean is 0 and the standard deviation is 1. But then Z2, inverse norm, but then we have the area to the left, and so I'm going to shade that whole area to the left. It's all of this plus that little tail part. And so with that said, we know that the middle part is 0.95 because again that total area under the curve is 1, and then 1 minus 0.025 in the left and 0.025 in the right, we get 0.95. And so adding up those two values, or that total area to the left here, is going to be 0.975. The mean is 0, standard deviation is 1. On the graphing calculator, we need to go to second vars, go to inverse norm, and from here we need to type in the area to the left. For Z1, the area to the left is 0.025, comma, the mean, which is 0, comma, standard deviation, which is 1. Close your parentheses and select enter. Again, mean is 0, standard deviation is 1 because this is a standard normal distribution. To find Z2, we're going to go to second vars, inverse norm. The area to the left this time is 0.975, comma, the mean, which is 0, comma, standard deviation, which is 1. Close your parentheses and select enter. Make sure to round your answers correct to 2 decimal places. From the graphing calculator, for Z1 we get negative 1.96, and for Z2 we get positive 1.96. So think about why these two numbers are the same, but one is positive and one is negative. Remember that the normal curve is symmetric, meaning that the left and the right half are identical to each other. So those two values are going to be the same, but one being to the left of 0, so it's negative, whereas one is to the right of 0, it would be positive. The next section is 6.2, real applications of a normal distribution. So the difference between 6.1 and 6.2 is that it's the same material, but now it's going to be more of an application-based process. So you'll notice that there's no additional notes, it just jumps right into examples. So the example we have, it says the reading speeds of 6th grade students is approximately normal with a mean speed of 125 words per minute and a standard deviation of 24 words per minute, round 4 decimal places. So we know the mean is 125 and the standard deviation is 24. Part A says what is the probability that a randomly selected 6th grade student reads less than 100 words per minute. So let's go ahead and draw our bell-shaped curve. In the middle we put our mean, and we know that the mean is 125. And we're asked to find the probability that this is less than 100 words per minute. And so 100 is on the left side, it's smaller than 125, that mean. And less than means we're going to be shading this graph to the left. So in order to find that area or that probability, we're going to use normal CDF. And then normal CDF is going to start with our lower bound, upper bound, mean, and standard deviation. So since this goes off to negative infinity, we're going to use negative 1 E99, comma, where the shading stops, and then that's at 100. Means 125, standard deviation is 24. On the graphing calculator, we're going to go to second vars, normal CDF. Lower bound is negative 1 E99. So negative 1, E is second, comma, 99, then comma, our upper bound for this one is 100, comma, our mean is 125, comma, standard deviation is 24, close your parentheses, select enter. From the graphing calculator, we get 0.1488. Part B says what is the probability that a randomly selected 6th grade student reads more than 140 words per minute? So again, drawing our bell-shaped curve and putting on our mean, which is 125 in the middle. This time it's asking us to find the probability of more than 140 words per minute. And 140 is larger than the 125, so I'm going to put it to the right. And more than means we're going to be shading this graph to the right. And we're going to use normal CDF to calculate that probability or area. Our lower bound where the shading starts is at 140. It goes on forever to the right, which is infinity, which we call 1E99. The mean, which is 125, and the standard deviation, which is 24. On the graphing calculator, we're going to go to second vars, normal CDF. For this one, our lower bound is 140, comma, upper bound is 1E99. So select 1E, again is second, comma, and again it puts the E on your graphing calculator. 99, comma, the mean, which is 125, comma, standard deviation, which is 24. Close your parentheses, select enter, and then correctly round your probability 4 decimal places. From the graphing calculator, we get an answer of 0.2660. Part C, which is on the next page, says what is the probability that a randomly selected 6th grade student reads between 110 words per minute and 130 words per minute. So again, sketching our normal curve. In the middle we put our mean, which is 125. And this time it's asking us to find the probability between 110 words per minute and 130 words per minute. So 110 is less than the mean, whereas 130 is a little bit larger than the mean. So we're looking for that part between. So again, using normal CDF to calculate that probability. The shading starts at 110 and ends at 130. Our mean again is 125 and our standard deviation is 24. On the graphing calculator, we're going to go to second vars, normal CDF. Our lower bound is 110, comma, our upper is 130, comma, mean is 125, comma, standard deviation is 24. Close your parentheses and select enter. Make sure to round your probability correctly to 4 decimal places. From the graphing calculator, we get an answer of 0.3165. Part D says, would it be significantly high for a 6th grade student to read more than 200 words per minute, and why? So let's go ahead and sketch what that curve would look like. The mean of 125 is in the middle. 200 words per minute is to the far right. And shading that very small little area there. Remember that for it to be significantly high, it's going to have a very small probability. So our probability is going to be less than or equal to 0.05. So it would be really small, really unlikely. So we have to calculate that probability. The x is greater than 200 words per minute. And we're going to calculate it by using normal CDF. And our lower bound where our shading starts is at 200. It goes on to infinity, which we use 1E99. The mean is 125. Standard deviation is 24. On the graphing calculator, we're going to go to second vars, normal CDF. Our lower bound is 200, comma, our upper bound is 1E99, comma, the mean is 125, comma, standard deviation is 24. Close your parentheses and select enter. Notice that this one has an E in the answer, which again means times 10. So on the calculator, and writing this in scientific notation, we get 8.89 times 10 to the negative 4th, which means we have to move our decimal place 4 times to the left. So we get 0.000889. And rounding 4 decimal places, that 8, we look at the 8 to the right, and this is going to round it to 0.0009. And is this significantly high? And the answer is going to be yes. And the reason why is because the probability is equal to 0.0009, and that is less than that cutoff, which is 0.05. The example right below says the U.S. Air Force requires pilots to have a height between 64 inches and 77 inches. Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Part A says what percentage, this is just like probability, of men meet the height requirement around 4 decimal places. So let's go ahead and draw our normal curve. The reason why we're drawing this normal curve is because it tells us that it is normally distributed for heights. And so the mean is going to go in the middle. Our mean is 68.6 inches. And this is asking for us to find the probability that they meet that height requirement. And the height requirement is stated as being 64 to 77 inches. So 64 is smaller and 77 is larger. And so this is between, so shading that area between those two numbers. So we're asked to find the probability that x is between 64 and 77 inches. So we need to use normal CDF to come up with that probability. The shading starts at 64 and ends at 77. And our mean is given to us at 68.6 and a standard deviation of 2.8. On the graphing calculator, we're going to go to second, vars, normal CDF, type in our lower bound, which is 64, comma, upper bound, which is 77, comma, mean, which is 68.6, comma, and our standard deviation, which is 2.8. Close your parentheses, select enter, and then round your probability correctly to 4 decimal places. From the graphing calculator and rounding 4 decimal places, we get 0.9484, or writing this as a percent, so this is our answer as a probability, we get 94.84%. Again, moving our decimal place twice to the right. Part B says if the Air Force height requirement are changed to exclude only the tallest 2.5% of men and the shortest 2.5% of men, what will the new height requirements be? Round 2 decimal places. So again, we want the tallest 2.5% and the shortest 2.5% to be excluded. So drawing our normal curve and putting our mean in the middle, which is 68.6. The shortest 2.5%, I'm going to call x1. So this little area is going to be 0.025. And the tallest 2.5%, I'm going to call x2. And that's equal to 0.025. We're excluding them. So in order to find that value of x1, we need to use inverse norm. Remember, it's area to the left, and we know that 0.025. The mean, which is 68.6, and standard deviation, which is 2.8. And then to calculate x2, we are also going to use inverse norm. This time it's the area to the left, and remember, total area under your bell-shaped curve is equal to 1. So 1 minus each of those little tails of 0.025, we get that that non-shaded area is 0.95. So the total area to the left of x2 is going to be 0.95 plus 0.025, which works out to being 0.975. Our mean, which is 68.6, standard deviation is 2.8. On your calculator, you're going to go to second, vars, go to inverse norm. We need to type in the area to the left, and for x1, the area to the left is 0.025, comma, our mean, which is 68.6, comma, our standard deviation, which is 2.8. Close your parentheses, and for x1, we get our value and make sure around 2 decimal places. To calculate x2, we're going to go to second, vars. Go to inverse norm on your graphing calculator. This time the area to the left for x2 is 0.975, comma, our mean is 68.6, comma, our standard deviation is 2.8. Close your parentheses and select enter. Make sure to round correctly to 2 decimal places. From the graphing calculator, we get x1 to be 63.11 inches and x2 to be 74.09 inches. So these are the cutoffs. So anybody who is 63.11 inches or shorter would not be accepted, and likewise anybody who's the 74.09 inches or taller would not be included. In Chapter 4, we learned that probabilities are used to determine whether a value is significantly high or significantly low, and we've seen this multiple times already. But significantly high is going to be x or greater, whereas significantly low is going to be x or less, but both of these have a probability that is less than or equal to that 0.05. The example right below this says the University of Maryland Medical Center considers low birth weights to be those that are less than 5.5 pounds or 2,495 grams. Birth weights are normally distributed with a mean of 3,152.0 grams and a standard deviation of 693.4 grams. Part A says if a birth weight is randomly selected, what's the probability that it's a low birth weight? So we're asked about a probability here. It does give us a mean and a standard deviation. First thing to note is that there's a couple different units being used in this problem. It does say 5.5 pounds, but it also words it in grams. And since our mean and our standard deviation are given in grams, that 2,495 is the number that I would be using for this, since it's also in grams. So we're going to draw our bell-shaped curve first, since it does say it's normal. In the middle, we are going to put our mean, which is given to us. It's 3,152. And then we are asked for part A to find the probability that's a low birth weight. And low birth weight is up above is anything less than that 2,495 grams. So probability that it is less than 2,495 grams. And so to calculate our probability, we're going to use normal CDF. And 2,495 is smaller, so I'll put that number on here. Shading to the left since it is less than. And our shading starts at negative infinity, which again we're going to use our negative 1 E99. Shading stops at 2,495. Our mean is 3,152, and our standard deviation is 693.4. On the graphing calculator, we're going to go to second vars, go to normal CDF. We're going to type in negative 1 E99, which is our lower limit, comma, our upper, which is going to be 2,495. Comma, the mean, which is 3,152, comma, our standard deviation, which is 693.4. Close your parenthesis and select enter. From the calculator, we get 0.1717. The problem continues on. Part B says find the weights considered to be significantly low using the criterion of birth weights having a probability of 0.05 or less. So probability of 0.05 or less. So we're going to draw our normal curve again, putting our mean in the middle, which is 3,152. So a significantly low value is a probability that's really small. Significantly low means it's on the left side. I'm going to call this value x here and shade this little area, which is going to correspond to the 0.05 that was given to us. And so in order to find this x value, that weight that we need, we're going to use inverse norm. Area to the left is 0.05. Our mean is 3,152. And standard deviation is 693.4. On your graphing calculator, you need to go to second vars, go to inverse norm. The area to the left is 0.05, comma. Our mean is 3,152, comma. Our standard deviation is 693.4. Close your parentheses, select enter, and then round your answer correctly to 2 decimal places. From the graphing calculator, we get a weight of 2,011.46 grams. Is significantly low or less. It could also be smaller than this weight or less. The next section that we have is 6.3. This is sampling distribution and estimators. We now consider the concept of sampling distributions in statistics. Instead of working with a value from the original population, we want to focus on values of statistics, such as a sample proportion or sample mean, obtained from the population. So it says the idea is when samples of the same are taken from the same population, the following 2 properties apply. 1, the sample proportion tends to be normally distributed, and 2, the mean of the sample proportion is the same as the population mean. Sampling distributions of a statistic, such as sample proportion or sample mean, is the distribution of all values of the statistic with all possible samples of the same size are taken from the same population. Sampling distributions of a sample proportion is the distribution of a sampling proportion or the distribution of a sample variable p hat with all samples having the same sample size n taken from the same population. So p is our population proportion and p hat is our sample proportion. Behavior of the sample proportion. 1 says the distribution of the sample proportion tends to be approximately normally distributed, and the sample proportion targets the value of the proportion of the population in a sense that mean of all the sample proportions p hat is equal to the population proportion p. Next, below this, we have the sampling distribution for our mean. And this is the distribution of all possible sample means for the distribution of the variable x bar, with a sample having the same sample size n and taken from the same population. Notation that we are going to be using is mu is equal to our population mean and x bar is our sample mean. Behavior of the sample mean. The distribution of the sample mean tends to be normally distributed. The distribution tends to become closer to normal distribution as the sample size increases, and we'll talk about that a little bit more in the upcoming chapters. And 2, the sample mean targets the value of the population mean.